No, Genesis. I don't want you to explain the students what geometrical isomers are. I don't want them to be dependent on you because you would not be present with them always. What I want them to do rather is they should start visualizing what you would have shown them in their own brains. So today, you will not help the students for geometrical isomers, but rather I would instigate their minds to visualize what the geometrical isomers would be. Thank you. So now, we've just seen what conformational isomers were. They were the different spatial arrangements around a single bond. But similarly, if we talk about spatial arrangements about a double bond, that is a different type of isomerism. That is called as geometrical isomerism. These two isomerisms are a part of stereo isomerism. But the only difference being this was around a single bond, this is around a double bond. Now, when I have a single bond, I was able to rotate. So if there was a group on the top, it could easily come to the bottom. But if I put a double bond, now if there is a group at the top, will it be easily able to come down? No. If this wants to come down, then it would have to break this bond, because a double bond contains one sigma bond and one pi bond. And in order for the rotation to happen, the pi bond has to be broken. And is it easy for the pi bond to be broken? No. A very high amount of energy, that is 284 kilojoules of energy is required. Where will the atoms get that energy from? So that is why the double bond provides a restricted rotation or a hindered rotation. So if there is a group, while formation is stuck at the top, will be at the top, and the other one, if it is at the bottom, it will be at the bottom. Unless and until a flip happens, the bottom group comes to the top and the top comes to the bottom. But these are not part of conformations. But this would be two different isomers. Yes. Now, if I talk about a molecule such as C2A2B2 in space, I can arrange it like this or like this. Now, out of the two, this particular spatial arrangement is called as cis and this is called as trans. So that means geometrical isomerism can also be called as cis-trans isomerism. Right? Now, how do you classify something as cis or trans? For that, the first thing you should remember is a horizontal plane. Yes, you would have to draw a horizontal plane over here, and then if two groups which are same are on the same side of the horizontal plane, would be called as cis. Now for this, do you actually need two pairs of groups? If I have AA over here, I had BB over here, if I replace this B and put another one, will it be cis? Yes, it will still be cis. So for a cis isomer, it's not necessary that on both the sides the group have to be same. On either of the side, if a pair of atoms or group of atoms is same, then also this would be called as cis. And similarly, if the two groups are on the opposite side of the horizontal plane, then this would be called as trans. Now, if I have a molecule like this, AA on this side and BB on this side, will this be cis? No, this will not be cis, because if I draw the horizontal plane, neither cis, neither trans. But if I draw a vertical plane, then these are on the same side. But cis and trans isomerism does not work like that. So you cannot draw a vertical plane. You will always have to look around a horizontal plane, right? Now these are the cis and trans isomers. Now what is the condition that is required for cis and trans isomer to happen? There are two very important conditions that the compound must follow in order to show cis and trans isomerism. The first one, presence of double bond. If the compound has a double bond, it will show cis and trans. But the second condition also has to be fulfilled. And the second condition says that if two same atoms or group of atoms are attached on the same side of a carbon, cis-trans isomerism will not happen. Let's take a look. If I have butene, I can make this structure and this structure. CH3 on the same side of the horizontal plane, CH3 on the opposite side of the horizontal plane. So this is cis-butene and this would be trans-butene. But if I change the position of the double bond and talk about a position isomerism of butene, which will be but1ene, this would be the spatial arrangement and this would be the spatial arrangement. Now, can this be classified as cis or trans? No, it can't, because the first condition is being followed, that a double bond is there. But the second condition, take a look at this carbon. On both the sides, it has hydrogen. Both the sides, it has hydrogen. So two same atoms are present on the same side of the carbon. Geometrical isomerism is not possible. Now let me ask you a question. I have a compound like this, I have a compound like this. Out of the two, which one is the cis isomer and which one is the trans isomer? Think. Yes, this is cis and this is trans. So whenever there is a name or a nomenclature associated with a particular double bond, then just before that add cis. Like for the example, when we were doing butene, we added cis-butene and trans-butene. Similarly over here, before its IUPAC name, just add cis, and over here trans. That's it. If I take one more acid, you see, I've just flipped. This acid is actually called as the malic acid because this is the cis isomer, and this is called as the fumaric acid, which is a trans product. Will the properties be same? I don't think so. The geometrical isomers, the physical property is totally different, but the chemical properties are similar. Yes, focus on the word similar. They are similar but not identical. So malic acid and fumaric acid may have similar chemical properties, but they won't have same chemical properties. So this was our discussion about geometrical isomers or the cis and trans isomers. Should I complicate more? Are you ready? Let's see. If I have a compound like this, I was having A, B, B. I was saying this is cis. Now, if this is A, this is B, D, and E. All the four groups are different. Can they show geometrical isomers? You must be nodding your head. I would say yes. How? There is another system for geometrical isomerisms which is called as the EZ isomerism. Now, what is EZ isomerism? How do you classify EZ isomerism? We'll just take a look. Now, the EZ system is based on the assignment of priorities to the different groups or the atoms which are present on the carbon. Now, these priorities are assigned using the rules which was given by Kahn, Ingold, and Prelog, and that is why it is also called as the CIP rules. Now, these are the CIP rules. It's a whole story. I'll tell you the crux of all these rules. The crux is that a higher priority is assigned to the group or to the atom which has a higher atomic number. Now, when we are assigning the priorities, when we have atoms, figuring out which one has a higher atomic number is very easy. But if I have a group, then how do you assign the priority? For that, you start comparing from the atom which is connected directly to the carbon and then move outwards. And wherever you encounter the first point of difference, whichever atom is the first point of difference, there, whichever atom out of the two has a higher atomic number, then the entire group gets a higher priority. That is about it. Now in the next rule, if you look carefully, when there's a double bond or a triple bond, what you need to do is you need to bifurcate the bonds in a way that you get like this. Now if I open the bonds and when I compare these structures, the comparison becomes much more easier when it was in the double or the triple bond. Now in cis and trans isomerism, we were talking about the horizontal plane, but in the E and Z system, we will be talking about the vertical plane. Yes, if I have a compound like this, I will draw the vertical plane, and if the groups which have a higher priority of both the carbons are on the same side of the vertical plane, then they would be classified as Z. Yes, Z comes from a German word which is called as zusammen, meaning together. And similarly, if two groups which are of higher priority are on the opposite side of the vertical plane, they would be called as E. And E is again a German word which is called as Entstiegen. Now, how do you remember? E can be remembered as the word enemy. Enemies are always opposite to each other. So using this enemy word, you can remember. Now if I have a compound like this and like this, out of the two, which one would be E and which one would be Z? So let's mark the priorities. Over here, you see that this has a higher atomic number, so this gets a priority higher. So I'll mark this as 1 and this one as 2. Similarly over here, this is 1 and this is 2. So on the vertical plane, the higher priorities are on the same side. So what do you get? This would be Z. And similarly, this would be E. So if I take the examples, you can easily classify now which one would be E and which one would be Z. Now if I take one compound which has a group, now how do I know that out of the two, which one has a higher priority? So I'll start comparing from inside out. And when I do that, I find out that over here, there is a difference, because this particular point, it has carbon, and over here, it has hydrogen. So that means the first carbon which was attached to the double bond carbon has hydrogen, hydrogen, and carbon. In the other one, it has hydrogen, hydrogen, and hydrogen. So which gets a higher priority? This group gets a higher priority. And similarly, you can assign the priorities over here. And this would become a E isomer. Now there is a very big misconception that people have. What is that? Now they will always say that cis can be equivalent to Z, because cis also is on the same side and Z is also on the same side. And E can be correlated to trans. But is that correct? Let's take an example. I have an example like this. If I check the horizontal plane and assign, what do I get? I get a cis product. But if I assign the priorities, this comes out to be E. So please don't generalize by saying that E would be equivalent to trans and cis would be equivalent to Z. Please don't generalize. Now only complicating one more time, if in a particular compound, if I have two double bonds, then what do I do? You don't have to worry. Just fix one double bond as your reference, assign the priorities. If the groups are different, if the groups are same, then you can also have cis and trans. But if over here the groups are different, So I'll use this as my reference point and the other double bond as my reference point, assign the priorities and find out what exactly is there at the first double bond and the next double bond. So if you look carefully over here, at the first double bond, it is having a E isomerism, and on the other one, it is having a Z isomerism. So what should be the name? This is how the name for this particular compound would be written as. So this was our discussion about E and Z isomerism, and with this, we come to the end of geometrical isomerism.